Welcome to video 6.2. We're going to talk about mole ratios, molarity, heat, and stoichiometry. Please read chapter 9 and look through sections 1, 2, and 3. And then there's a self-check exercise on called 9.4 on page 248. All right. The answers are in the back of the book so you can see. And then some other pages to look at. So please do that. All right. So, look at these cute dogs. They're going to tell you some real-world connections to chemistry. Yay. All right. So, a lot of times when we look at water, we're thinking it's pure, but it's not. It's usually a solution, meaning it's a homogeneous mixture. There are all kinds of solutions, and every solution has two parts: the solute, which is the thing that is dissolved or mixed in, and the solvent is what it's dissolved into or mixed into. A lot of times we talk about water being a solvent. Miscible is when we talk about two liquids that mix together. That mix. Okay, so like water and vinegar. Oh, look, it's Kool-Aid. Here's a solution. So it's time to concentrate now. Realize that a solution is the solute and the solvent together, so it's a mixture, so it's two parts. And then how do we describe a solution is we usually talk about how much solute is in there, and that's the concentration, how much solute is in a solvent. So we have our solvent and we have our solute, and it's really well mixed, and you can't see the parts. And concentration describes how much is in there. And so we're going to look at how many moles of solute are in a liter of solution. And that's what we're going to use to describe our concentration. That is called molarity. Okay, molarity. Now you've encountered molarity a lot already because molarity is how many moles of solute in liters of solution, right? Because remember, solutions are mixture. Right? So molarity is the moles per liter. Right? So it's a split unit. It's kind of like density, which is grams per milliliter. Molarity is moles per liter, and it's given a capital M. So memorize the formula for molarity. Capital M equals moles per liter, and it's moles of solutes over liters of solution. Liters of solution. Okay. So what does 5 capital M mean? It means 5 molar HCl. That means there's 5 moles of HCl, hydrochloric acid, for every 1 liter of solution. Right? It's a ratio. Right? So we can calculate molarity if we know two things, the moles and the liters. So there's 2.5 liters. So this is the volume of solution. And there's 45 grams. So this is the solutes. But we need molarity, moles per liter. So we have to change that 45 grams of NaCl into moles of NaCl. So we cancel out grams, get the moles. This is NaCl the whole time here. NaCl. 1 mole of NaCl. How do we know how many grams are in a mole? We go to the periodic table and we get Na plus Cl is 58.44 grams. All right, 45 divided by 58.44 is 0.77 moles of NaCl. So to get the molarity, we need the moles, 0.77 moles of NaCl over 2.5 liters of solution, and the molarity is 0.31 moles per liter, or 0.31 capital M. All right, let's do another one. How many grams of calcium chloride must be dissolved to make 25 milliliters of 3.5 molar solution? Okay, so this time, what are we looking for? We're looking for how much solid to put into the solution. We need to find grams. All right. And so we're going to start with what we know. We know we have 25 milliliters of solution, and that there's 1,000 milliliters in every 1 liter. Now you might be saying to yourself, why is she changing milliliters to liters? because the definition of capital M is mole per liter. So anything we do with it has to be in liters. Okay. Now, every time we have 3.5 moles, we have 1 liter. So I want to find out moles, how many moles I have going in. So I know that 3.5 moles for every 1 liter of our solution is going to give us however many moles are in that 25 milliliters. And then I know that this is a solution of calcium chloride. So for every 1 mole of calcium chloride, I need I know there's 110.98 grams of calcium chloride. You might be saying to yourself, Self, where'd you get that? This is from the periodic table. So look what happens. Milliliters cancels mills, liters cancels liters, moles cancels moles. And I find out that I have 9.71 grams of calcium chloride in this solution. So here's what this means. Here's a container, right? Inside this container is 3.5 molar calcium chloride. Right, now someone took 25, so measured out. Oh, look, it's a graduated cylinder. 25 milliliters of that was poured into here, okay? And so then, how much this is how much calcium chloride is dissolved in that solution, okay? That's what that means. So then we know how many moles of calcium chloride are in there, and then we can change that to grams. Okay. So stoichiometry, fun word. Try it. It's the mathematics of chemical equations. So we're going to be using recipes, chemical recipes, and we want to know if I put in 50 grams of salt and 3 crackers, how many Cheez-Its am I going to get out? That mouse sure wants to know. So you need to have a few things. You need a balanced equation. You need given amounts in grams or liters or milliliters of solution. You know, you have to look at what you're trying to find, and you definitely need a periodic table. So I'm going to give you an analogy about tricycles because they're fun. There's a formula for making tricycles. You need 3 wheels and 1 frame for every 1 tricycle. So here's a problem. If I have infinite number of frames, all the frames I could use, how many tricycles can Ariana make with 9 wheels? Okay, so here's how you do this. We say we got 9 wheels going into this tricycle reaction. And every time we use 3 wheels, we'll get 1 tricycle. Okay, so look, wheels cancel wheels, and we're left with tricycles. So we know that we're going to make 3 tricycles. Oh, how do you spell tricycles? Okay, that's how I spell it. 3 tricycles can come out. Right. So if 9 wheels go in, 3 tricycles can come out. So that means that this equation is about parts. 3 parts to 1 part equals 1 tricycle. Okay. How is that related to chemistry? Well, in a chemical reaction, oh look, we have one here. The chemical equation is related to parts. What kind of parts can you have? Well, you can have molecules or atoms or formula units, and you can have heat. Those are the parts of a chemical reaction. And so these parts, these coefficients for the parts of a chemical reaction mean moles or they mean kilojoules. And if you don't see anything, you know it's a 1. So we can use these as conversion factors. So what this balance equation means is that 3 moles FeO equals 2 moles of aluminum, because I use the coefficients, and only for this reaction though. Also, 3 moles of FeO equal 1 mole of aluminum oxide for this reaction. So the coefficients mean equalities based on this chemical recipe. So we can use these as conversion factors. So 3 moles FeO for every 2 moles of aluminum, or we can say 2 moles of aluminum for every 3 moles of, I meant to say FeO here, FeO. Right? You could take this and write 2 conversion factors. So we finally have the power of changing one chemical substance into another one, or changing a chemical substance into heat by using these coefficients to represent the moles. Okay? So you can change one kind of substance into another as long as you have a balanced equation and use it as a mole ratio. So in this, I'm given 12.3 grams of KClO3. I want to know how much oxygen will come out of the reaction. So find oxygen, grams of oxygen. But wait, these coefficients are moles. So if I take the 12.3 grams of KClO3, potassium chlorate, and I turn it into moles of KClO3, I can do this by using the periodic table. And when I use the periodic table, I'm finding the amount for 1 mole. So then I look at K and C, and, Cl and 3 O's, and I find out that I get 122.55 grams of KClO3 for every 1 mole. Now that I have moles, I can use these coefficients to change these into these. So I would put moles of KClO3 on the bottom because I want to get rid of it. Change it into moles of O2, put that on top. Okay. And then if I want to find grams, I have to change moles of O2 into grams of O2. So we're using conversion factors. We got to let the units guide us. And this is the important step. This step is called the mole ratio. Mole ratio. And the place you get the numbers for the mole ratio are the coefficients. So that's why I have to label these. So I go in with KClO3. So these kind of moles, there's 2 of them, coefficient of 2. And I come out with oxygen. So this coefficient is the one that goes there. And then I change one chemical into another. So my final step, I could say for 1 mole of O2, I'm going to use 32 grams. And that came from the periodic table. Okay. Then you plug this into your calculator. 12.3 divided by 122.55 times 3 divided by 2 times 32 gives us 4.282 grams of oxygen. Okay. So what this means is if I put in this much of KClO3, I should be able to get out 4.82 grams of oxygen. Pretty cool. Changed one chemical into another. Oh, look, it's another problem. This time I have 4.3 grams of KCl3 going in. I want to know how much KCl will come out. So I have to change one chemical into another. So I start by putting the grams of the given KClO3, and I have to change that into moles because the only place where you can change the chemical identity of a substance is if you're in moles. And so here's where I can. Moles of potassium chlorate going in. Moles of potassium chloride coming in. Excuse me. And then I can change my moles of potassium chloride into grams of potassium chloride. Okay? So look at all these units. Grams are going to cancel. Moles of KCl3 will cancel. Moles of potassium chloride will cancel. And I'll be left with grams of potassium chloride, which is what I was looking for. All right, so numbers. Anytime it's moles and grams, the chemical identity is the same. 1 mole equals grams from the periodic table. Anytime it's one kind of mole and another kind of mole, the numbers have to come from the coefficients. So there's a 2 right there, and a 2 right there, KClO3 and KCl. Anytime it's grams and moles, moles are number 1, and grams come from the periodic table. So I add up potassium chloride, and I get 74.99, because that, 74.55. Okay, so grams cancel, moles of potassium chloride, moles of potassium chloride, and then when we put it into the calculator, we get 2.76 grams of potassium chloride coming out. All right, we're going to keep going. This time I have this many grams of O2 going in, given, all right? And then I want to know liters of CO2. How many liters of CO2 are going to come out? So I have to change oxygen into carbon dioxide. The only time I can do that is if it's in moles. So I say my 5.67 times 10 to the third grams of O2. And so I have to get that to moles because you can't change the chemical identity unless you're in moles. Right? Then, now that I'm in moles, I can change moles of oxygen into moles of carbon dioxide. Now this problem wants me to come out with liters. So to change moles of carbon dioxide into liters of carbon dioxide. All right, numbers. Anytime it's moles and grams, moles are number 1, and the grams come from the periodic table. Anytime it's moles of one kind and moles of another, I use coefficients. So you don't see it, but there's a 1 there. And you do see it, there's a 2 there. Boom, right there. And then the 1 is right there. Okay. Liters and moles. Oh, it's been a while since we did that, but anytime it's carbon dioxide, 1 mole is 22.4 liters of gas at STP. Okay. Grams of oxygen go, moles of oxygen go, moles of carbon dioxide go. Boom, liters of carbon dioxide left. You get 7,938 liters of carbon dioxide. Yay. All right. Uh-oh. This time we have molarity. Luckily, we just learned it. Okay. So we need a balanced equation. And so we have this much silver nitrate going in. We want to know how much grams of barium nitrate coming out. Grams coming out. Okay. So this time, since this is a solution, we have moles per liter, and here's our milliliters. We have to take our 250 milliliters of silver nitrate solution and find out, well, for every 1,000 milliliters, you get 1 liter. And then, according to malaria, this capital N means that for every 1 liter of silver nitrate solution, there's 1.5 moles of silver nitrate. Okay. So notice, this is silver nitrate solution, this is silver nitrate solution, this is my 1.5 M. Now I'm ready, because this is moles, to change moles of silver nitrate into moles of barium nitrate. And then the last step is hopefully familiar, moles of barium nitrate to grams of barium nitrate. So, numbers for moles of one kind and moles of another have to be coefficients. So there's a 2 in front of silver nitrate, so I have to put a 2 down there. Coefficient. Coefficients. Right? And then there's a 1 in front of barium nitrate, so I have to put a 1 there. Okay. And then 1 mole of barium nitrate, I have to go get grams from the periodic table. And when I do that, I get a big number, 261.35 grams of barium nitrate. So let's see what happens. Milliliters of silver nitrate cancel. Liters cancel. Moles of silver nitrate cancel. Moles of barium chloride cancel. I said chloride and not nitrate. And so then I just do 250 divided by 1,000 times 1.5 divided by 2 times 261. And I find out that 49.00 grams of barium nitrate should come out of that chemical reaction. All right. Hey, what about heat? Heat can act like a coefficient as well. It's kind of a heat coefficient. So moles and heat are related based on a chemical reaction. Okay. Here's one where it is. So the question is how much heat, so we're finding heat, decomposing 58 grams of potassium chlorate. So 58 grams of this, 58.6 grams of this goes in, and then how much heat comes out? Well, that means we have to change potassium chlorate into heat. So we start with our 58.6 grams of potassium chlorate, and we change grams of potassium chlorate into moles of potassium chlorate, because you cannot use a chemical reaction unless you're in moles. And then, or heat. And then we can change moles of potassium chlorate into kilojoules using the coefficients, right? So moles and grams, moles are number 1. You got to go get grams from the periodic table, 122.5. All right, moles and heat. It's a little bit different, but it's from the balanced equation. So I have to use the 195.3 kilojoules, and I have to use the 2 for moles of potassium chloride. Right? So I multiply this, divided by that, times that, divided by that, and I get 46.69 kilojoules of heat released. Okay, this one's different. It's heat's going in this time. Heat, given heat. Liters of O2 should come out. Okay, so we want to know how many liters should come out. So I'm going to put 28.85 kilojoules of heat going in. Since heat's part of the equation right there, then I can use kilojoules right away and go to moles of oxygen. And then once I have moles of oxygen, I can do liters of oxygen. All right. Moles and kilojoules are kind of like moles and moles. There's a coefficient. So it's 195.3 from the equation and a 3 for oxygen. And then 1 mole is 22.4 liters. That's the definition of a mole. kilojoules cancel, moles of oxygen cancel. We're left with liters, 9.93 liters of O2. I know this is a lot of problems, but you got to look at some examples to understand how to do it yourself. Okay, so here's two more problems that I'm going to save for when we get to class to do practice with. But if you want to try them, which I recommend, try them. The answer for this one is going to be the 968.78 grams of iron. Okay. And then the answer for this one is going to be 6.07 grams of aluminum. Try and see what you can do with them. But here's the main idea. Coefficients in a balanced equation are ratios, and you need to use them to change the identity of one chemical in another to another. But the ratios only work for moles to moles, heat to moles, and moles to heat. All right. The grams have to be changed to moles before you can use the coefficients. All right, review. Go through moles to change one chemical to another. Use your moles as coefficients. Use your coefficients as moles. You have a ratio of moles of one kind and moles of another. You can change reactants to products, products to reactants, reactants to other reactants. Wow. You can also use heat-mole ratios. And then don't forget about molarity. It's a concentration. And you can calculate it, or you can use it as a conversion factor. Hey, this math might help you. So if you get a chance to print this out, here's the part where you would use coefficients. Okay. And so we'll keep working on it. Hopefully you got some notes, and then when we talk about it in class, you'll get it. All right, don't forget, Chapter 9 is fine. And here's what I hope we can do after we are done studying this unit. Peace out. Don't forget to hit the target.